Welcome everyone to GeoHug. So before we kick off today's session, I'd like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, this is going to be a fun one. I am super excited that we have Scott Halley joining us today. So Scott needs no introduction as the legend of all things geochemistry, but he is a consulting geologist specializing in geochem. And now that he's working part-time, he's also an associate researcher at Codes at the University of Tasmania and also teaches the occasional geochemistry workshop. And today is going to be absolutely epic as we get a live demo in ioGAS using geochemical data integrated with logged rock types to make a more consistent geological interpretation. So I hope you all enjoy it. There's so many of you online already. I'm going to promote everyone that I can up as panelists. Please don't be shy. This is your chance to chat with Scott directly, ask questions once we've finished with the presentation. But yeah, it's going to be a lot of fun. So thank you so much, Scott, for joining. It's absolutely brilliant having you here.
Thanks for inviting me.
So good. I was curious what got you into geology to begin with.
Wow. When I was at primary school, my grandmother was right into collecting gemstones, cutting and polishing gemstones.
Yeah.
So when I was a little tagger, I'd go out on weekends with my granny. We'd be out in the bush looking for petrified wood and agate and panning in creeks for big red zircon crystals and spinels and whatever. So I was hooked from the time I was about 5, I think.
Oh, I love that. That is so cool. And yeah, you have so much experience in the industry now. What are some of your favorite highlights so far?
Favorite highlight to be people I've worked with. One of my early jobs was with a company called Renison Goldfields Consolidated, RGC. We thought it stood for really good company. And one of the guys I worked with there was a fellow named Simon Gatehouse, who I think is the smartest geoscientist I've ever worked with.
Yeah.
Simon wrote the original version of ioGAS. Well, it was called GAS then, stood for Geochemical Analysis System. That was 1991. So working with Simon was amazing. I learned so much from him. And then RGC was, they split out their gold assets into the Australian version of Goldfields. And then they merged with Delta and became Orion Gold.
Yeah.
And then Orion Gold was taken over by Placidome. And then I worked with Greg Hall for a long time. And working with Greg was pretty sensational as well.
That is awesome. I love that. That's yeah, some awesome experiences that you've had there. And I bet you've collected pretty good pet rocks along the way. Which ones have you bought for us today?
I've only brought one today. I better.
Oh, yeah. Perfect.
So that rock there
Yeah.
is a piece of abducted ophiolite that came from the border between Italy and Switzerland at the foot of the Matterhorn. And there are massive big slices of ophiolites running through underneath the Alps. And they're full of anchorite and pyrite. So that's a basalt with molinetic textures and anchorite and pyrite. And I would love to have smashed off bits of that and put them in sample bags and assayed them. But
Yeah.
that was on a trip when I walked around the Matterhorn. It was 180 kilometres in 10 days, camping out all the way. That was pretty cool.
That is awesome. Oh, I love this. Well, thank you so much, Scott. It is awesome having you on today. If you want to share your screen and yeah, let's get stuck into it.
Okay, I'm going to take a big risk today and do a live demo in ioGAS. This is a cross-section from a porphyry copper system from an unknown location. And what I want to do is show you how I integrate logging data with chemistry. What we normally see, if you try to build a geological model based on logging data from a mine site, you see all sorts of inconsistencies in the logging. And it's, because you have lots and lots of geos over a long period of time, all with different levels of skill. So it's really hard to make good geological models. This particular data set here was all relogged in a single campaign by one of the best geological teams I've ever worked with. So the logging data here is really consistent. So you won't see too many discrepancies in the logging, but you will see things that these really, really good experienced geologists could not pick visually, but we can pull out from the chemistry. So I'll give you a bit of context to start with. I will look at this data in 3D. Hopefully you can see all of that okay. To start off with is I will show you where the copper is on this cross section. So I can select copper, 10 equal bins. I'll do a linear color stretch, auto attribute. Okay, so you should be able to see some pretty decent copper grades in a porphyry system here now. So this is just looking at a cross section of the drill hole traces. All right, so that's copper grades. So there's a big volume of rock in here that's over 0.5% copper. I could color that by moly. And what you'll see is the moly is a halo to that copper shell. All right, so see how most of the moly sits outboard from the copper zone? I could plot sulfur. And you see the top of the copper zone here does not have particularly high sulfur. Sulfur mostly sits on the flanks. A lot of the sulfur is leached out near surface, and a lot of this sulfur is anhydrite rather than pyrite. So just keep in mind where the main mineralized center is in here. And I'll close that. And now we'll go and see how the logging data correlates with the chemistry. So I'll go to the attribute manager. I'll delete all of those. And now I'm going to load a legend. So this is a data set that I've worked on a few times, and I've created a color legend and I've saved it. So once you have a saved color legend in ioGAS, you can reuse it whenever. So I can open this legend. I can load the saved colors, shapes, and sizes for the attributes. And I'm going to use this auto attribute function. And I'm going to color the points by the logged rock type. Okay. So now if I look at that section, these are the logging names that the geologists have assigned to each assay interval. Except I've got a bunch of holes here that have not been, or where we don't have logging data. So I can look at that in the cross section, add a legend. All right, so that's what the log geology looks like. So far, so good. What I'm going to do now is see how the logging matches the chemistry. So when I look at porphyry copper systems, I look at the same kind of immobile trace element plots every time. And I can save that Geochem plot scheme. So I've got a thing here called a template. I can open a recent template, porphyry copper compositions. And it automatically regenerates all the plots that I've been using. Oh, there's some fantastic shortcuts in ioGAS. So I'll show you the plots that I've generated. First of all, I'll plot a bunch of trace elements against scandium. And the reason why I use scandium here is because scandium is highly correlated with the amount of iron that's hosted in silicates. But scandium is relatively immobile. So if the iron is doing funky things as the rocks are being altered, scandium will just stay where it is. And I'm going to plot a bunch of immobile trace elements against scandium. So here I've got titanium, thorium, vanadium, yttrium, niobium, and phosphorus. Now, some people will ask why I haven't used zirconium. This particular porphyry system is 20 million years old, and zircons do not dissolve very well in a 4-acid digest. So the zircon numbers here will not be usable. Another plot I'll use is the same list of elements, but I'll put titanium first. So titanium is going to be in the opaque oxide minerals. It'll be in rutile, maybe ilmenite, titanite, and maybe a little bit in hornblende. So we're seeing how the amount of opaque oxide compares with those same immobile trace elements. I'm going to plot this diagram, which is pre-programmed in ioGAS, and everybody who ever explores for porphyry systems uses this. One of the characteristics of porphyry copper magmas is that they have a really low yttrium content. And I think that's primarily because yttrium is taken up in titanite. And all porphyry copper magmas fractionate titanite. So as they fractionate, the yttrium goes down. And porphyry magmas also have high strontium because the magmas evolve in pressure, temperature, water conditions that for the most part are above the liquidus temperature for plagioclase. So when plagioclase fractionates, especially the sodium-rich end of plagioclase, it removes strontium from the melt. So porphyry copper magmas, as they fractionate, will go to lower yttrium, but a high strontium-yttrium ratio. Another plot I'll use in porphyries is this. I'll have to zoom the data. This vanadium-scandium ratio is sensitive to oxidation. That tells you something about the oxidation state of the magmas. So the average for the whole of the Earth's crust, vanadium-scandium ratio, is 7:1. Magmas that fractionate magnetite, the vanadium will be sequestered into the magnetite, so the ratio decreases. If it's an oxidized magma, then vanadium is a little bit incompatible in the silicates. So as they fractionate pyroxenes or hornblendes in an oxidized melt, the vanadium-scandium ratio increases. So we'd expect the background down here around 7 somewhere. So all of these things in here got really high vanadium-scandium ratios. It tells us that these magmas, or the provenance of the sediments, has been from a really oxidized source. And one other thing I'm going to look at is this. I'm kind of interested in the aluminium content. I'll put a point density contour overlay on that. Most igneous rocks will have an aluminium content of around 6 to 8%. And that's because the aluminium is going into feldspars. It'll be calcium-rich plagioclase in mafic rocks. It'll be alkali feldspars in felsic rocks, but it's always about the same. These ones are lower than usual because this is a pretty alkalic basalt. These ones in here is one of the porphyries, and that has high aluminium because it has not fractionated plagioclase. So a lot of the aluminium has stayed in the melt. I'm really interested in this because there's some types of alteration where calcium, sodium, potassium, magnesium, etc., are removed from the rock, and it causes a residual enrichment in aluminium. It's not because aluminium is being enriched, it's because other things are being taken away. So sometimes we'll see advanced geologic alteration popping up in here somewhere. In other cases where rocks have a really high abundance of quartz veins, or where they're brecciated and infilled with quartz or carbonate, the effect of that space-filling material, quartz carbonate, will be to dilute all of these immobile elements. So this tail of stuff in here, I am pretty sure will be rocks that have a really high vein density. So I'm going to watch out for that stuff in the other plots. So we'll just go and look at one of these things. Let's look at the scandium plot. And I'm curious to see how these guys have logged the rocks. Have a look at this phosphorus plot, scandium versus phosphorus. The things here in green are all logged as mafic rocks of some sort. And you can see there's different populations in there. Like there's quite different lithologies have been logged as mafic rocks. We'll look at some other things. We'll go all invisible, turn on this porphyry. Right, I'm just looking for populations in the data, but you can see here that there are two different populations that are logged as the same crowded hornblende porphyry. And there's a little population here, stuff with slightly higher niobium. That'll be this one here with higher titanium. Right, so there's a few inconsistencies in the logging, and I'm going to try and use the chemistry to assign these unlogged rocks to the right group, and to remove some of the inconsistencies in the logging. So we'll go back to all visible, and I'm going to start by picking the things that are really, really obvious, and then working my way through to the things that are pretty difficult. So I'm going to pick these mafic rocks first, and I think the best plot to identify those will be this titanium versus phosphorus plot. So I can right click on this window to enlarge it. And there are a few green points that are hidden down in here. So what I'm going to do is in the attribute manager, I'm going to add a new group. I'll make it green. I'll call this mafic. And I'm going to make a polygon and lasso all of these things. I'll put these high phosphorus ones in. Okay. Now, unless you look at a lot of geochem data, this won't be obvious to you, but this is a mafic rock with really high titanium. This is like a lot higher than we'd see in an Archean basalt or in a mid-ocean ridge basalt. But these are crazy high phosphorus numbers. And not only are those phosphorus numbers really high, but these are super high niobium numbers as well. This is not a normal basalt. This is an alkalic basalt. And it's kind of unusual in this part of the world. There's a few other things we can pick out of this. I want to pick out these high phosphorus things as a separate group. So I'll add a group. I'll call it mafic high phosphorus. And I'll make them a different color. And I'll pick these guys. Okay. And then I'm going to look at a plot of scandium versus nickel. I could have plotted chrome instead of nickel, but I chose nickel because I know that not all of the chrome will dissolve with a 4-acid digest. But normally chrome and nickel will be pretty highly correlated. So I'm going to add another group and pick these high nickel samples. So I'll call this mafic high nickel, and I'll make those purple. and I'll lasso these guys. Now, I'll digress here briefly. If I go to this diagram, I'll just go all invisible and I'll turn on these mafic groups. I know that the average basalt should have a vanadium-scandium ratio of about 7. These things are kind of like 7 to 15, even up to 20. Like these are crazy high vanadium-scandium ratios. This is a mafic rock that has fractionated pyroxenes. It's fractionated lots and lots of pyroxene. And it is so oxidized that vanadium is showing incompatible behavior in those pyroxenes. What I can see from this is that there's a section of the mantle underneath this deposit that has an anomalously high oxidation state. And this is something I've seen all through the East Lachlan in Eastern Australia. I've seen it in British Columbia. I've seen it in the Maricunga Belt in Chile. The classic case of this is Porphyry. Where we see these gold-rich porphyry systems, there's evidence like this that indicates an anomalous high oxidation state in the mantle. And that's why I like doing all of this rock classification manually rather than using some kind of numerical analysis. So I'll show you where these things occur spatially. Here's my cross section. And I'll turn off those points. I don't know how well we can see this, but here's the main volume of that mafic material is in the green color. Underneath, I've got this khaki color in here. So these are the high phosphorus things. And underneath that is this high nickel thing. So all of these were logged as mafic rocks, but actually we can see 3 different eruptive units in there. So we are defining stratigraphy from the chemistry that the geologists could not pick in their visual logging. I reckon that's pretty cool. Okay, so what I'll do now is turn everything back on. And next I'm going to pull apart the rhyolitic rocks. So I'll turn off these mafic things. And I'll go to this. So what we have now is a bunch of sedimentary rocks in the greys and the pale blue. We've got things logged as porphyries in these warm colours, and we've got things logged as rhyolites in these yellows and pinks out here. Porphyry copper magmas typically have titanium values between 0.2, 0.3, 0.4% titanium, and they have low thorium, low niobium, low yttrium, low lanthanum and cerium. And that's because all of those high field strength elements are taken up into titanite. And as titanite fractionates from the melt, it removes those elements from the magma. Mid-crustal melts don't crystallize titanite. So all of those things like niobium and thorium, lanthanum, etc., remain as incompatible elements. So as the silica content goes up, thorium, niobium, etc., increase as well. So all of these high thorium things in here look like they've got a really, really different magma source to these porphyries. So I'm going to make a new color group. I'll delete those ones because I've reassigned the mafic rocks. So delete. I'll make a new color group. I'll call it rhyolite. And I'm going to pick all of these high thorium ones. What did I do then? Oh yeah, I've got to change the color. I'll make those yellow. Okay. What I can see now is that there's a subset of these yellow guys that have low vanadium. That's kind of interesting. If I go to the vanadium-scandium ratio, that's these things in here. Right, so there's one of these rhyolite units has come from a condition of pressure, temperature, water content where magnetite has crystallized early and has resulted in this stuff being depleted in vanadium. So this has got to be a low pressure mid-crustal melt. So I'll call this fractionated rhyolite. And I'll give them some different color. And I'll select them with a polygon. All right, so remember that kind of background vanadium scandium value should be around 7. So these ones are really depleted. And now if I go back to the titanium thorium plot, it looks to me like there's two populations in here. There's one population with really high thorium and one not so high. These things are almost certainly going to be fragmental rocks and maybe volcanoclastics because they're not plotting as a tight cluster. When you see a big scatter like this, you know it's a heterogeneous rock. It's likely to be fragmental rather than something like a lava or a porphyry. So these are probably volcanoclastics. So in the attribute manager, I'll turn those off and I'll make another group. I'll call it rhyolite high thorium. And I'll make them some kind of orange color. And I'll make a polygon. Okay, so now we'll see where they are. I'll just go all invisible and I'll turn on these rhyolites and I'll have a look in 3D. Okay, now there's a few things here that I've misclassified, right? So all of these classification schemes will not be perfect. If I get 90% accuracy in this, I'll be pretty happy. But those things are probably porphyries that I've misclassified. But you can see this orange one here with the high thorium is sitting above that kind of moderate thorium group. And then the things with the vanadium depletion are sitting way down in here. So these things were actually logged as basement rhyolite originally. There's a few points I've missed. It's probably these things in here. We'll just see if that's actually true or not. If I pick these, window 3D, yep, it was those. All right, so you can see we've picked out compositionally 3 different types of things where previously we had 2 rhyolites logged. So far, so good. I'll go back to the attribute manager. I'll turn off these. What I'm going to pick out next are the sediments. If I put on a point density contour on this, we're just looking for the populations in the data. So this population of stuff in here on the scandium titanium plot, so these things have higher scandium, higher titanium. It means they're more mafic. There's more iron in these rocks. These are the things that were logged as sediments. That group in there, okay? So some of these, if I look at the attribute manager, some were logged as an epiclastic conglomerate, and some are just logged as sedimentary unit, whatever that is. Just delete that one. With the chemistry, I can pick the compositions, but I cannot pick textures. So I can't tell what the grain size is. I can't tell if that's a conglomerate. I'm going to trust their logging and just keep that epiclastic conglomerate sequence as it is. I'll turn those off. But now I'm going to take the rest of this group, the rest of these things in here, and add them into the sediment unit. There's a few grey points down in here that might have been mislogged. So I'm going to add another group. I'll call it sediment. I'll make them grey again. And I'll draw a polygon around these. And now if there are any ones that were left over in here, I'll delete that and they'll revert back to the unclassified group. Okay. So what we have left over now is pretty much just all the different porphyries. I'll put on a point density contour and we'll look for groups in here. There's one weird group, this little group in here with really low yttrium. They are pretty unusual. And there's another really coherent group up in here. So I'm going to pick out that one and see where they occur and just check how they've been logged. So I'll make another group. I'll call it porphyry. Porphyry with low yttrium. And I'll make them a different color. And I'll select the polygon. And then I'll turn those off. Now we'll have a look at the point density overlay again. This group in here is logged as, most of those are logged consistently. It's this one, pre-mineral sill, like that pale pink group. Right, that's a really coherent, really homogeneous unit. Which of those plots defines it best? Doesn't matter. We might pick it off this titanium vanadium plot. So I'll add a group. I'll call it make them pale pink color. And I'll use that as a guide. And then in the attribute manager, if there are some of those that are misclassified, I'll delete that and they'll go back to the default color. Turn that off. So this is what we've got left now. These things have all got really similar compositions. It's pretty hard to see any differences in there. I'll change this. I'll look at scandium first. There's two main porphyries are logged in here, this red group and this magenta group. And I can see a subtle difference on the scandium titanium plot. And I can see a bit of a difference on the scandium thorium plot. Right, there's a bit of a difference in the niobium contents, but niobium is highly correlated with titanium, so not really independent things. And we've got this tail of low points in here. I think this is a dilution trend. I think these are rocks that have a higher vein density. So sometimes it's not always obvious on a binary plot. I'm going to try a ternary plot. The things that seem to show the best differentiation are titanium, scandium, and thorium. So what if I go select variables, titanium, thorium, scandium. Okay. Now the titanium numbers are really low because they're in percent values, but I'll do a ternary. They all plot down this side because the titanium numbers are really low. There's a little tool in ioGAS for the ternary diagrams where you can do skewed axes in here that plots the data in the center. And then I can put a point density contour on that. And I think we can see two different populations in here. Right, so I'm going to pull those ones out separately. I'll do a magenta group. So somewhere in here. And then I'll turn those off. And then I'll do a regular porphyry. And I'll make all of those red. And I'll put everything else into this red group. And now I'll go all visible. I'll get rid of these empty cells. So if I was doing this as a consulting job, I could have used titanium, thorium, scandium, and pretty much classified all of those rock types just using that ternary. So I could have created a customized discrimination plot for this project that would have allowed the guys to come in, select the diagram, and then auto classify the points on this figure. But anyway, that's for another day. So now let's go and look at this stuff on the cross section. And even though these red and magenta things are so similar chemically, you can see there's two different intrusions. This magenta one at the bottom, where most of the grade occurs, and this red one at the top. Right, so there's two different porphyries up the same plug hole, but the magenta one is more fractionated and it's associated with most of the metal in this system. So that's kind of an amalgamation of the logging data and the chemistry. This stuff still isn't exactly right. In the real world, you'd come back here, I would come back here, and I would go back to the drill holes and find this stuff in the core and pick visually what the differences were. The other thing I know is that a lot of the grade in here sits around the top of this magenta porphyry and it's hosted in breccias. So a lot of these things were logged as breccia, but when we plot the chemistry, you can still see the original volcanic stratigraphy going straight through. So even though these rocks are brecciated and fragmented, there's been very little displacement in those rocks. We can see where the grade occurs. If I go copper, let's do a split probability plot. And it shows us the copper grade divided by rock type. So you can see the high copper values in this magenta one in here, but the highest grade is where this thing cuts through the basement rhyolite and where the pink thing intrudes into these felsic rocks. So that's where most of the brecciation occurs and where the highest grade drops out. Right, so there's lots of things that still need to be validated, but imagine if we had this kind of data for every hole in this deposit and then used this as the basis for building a geology model. Like, this would give you a really, really robust geology model. And what we could do next, one last thing I would do is data, make variables from color. So I could call this composition. Okay. And now when I go and look at my data table in here, I've got a new column on the back end. It says composition text. So these are the names that we created. And then I could export this to Leapfrog or just export it as an Excel file for whatever software package I wanted to put it into. I think that's about it, guys.
This has been absolutely brilliant. Thank you so much, Scott. That was really awesome. I think everyone got so much out of today. So can't thank you enough for your time.